And then let's put those cell phones away. Oh. Okay, here we go, everyone. So with our different types of reactions, what we're going to be doing today is, once again, really trying to connect to the chemistry triangle of all three sides. Okay, so we're going to look at them symbolically, which is like the strips of paper. Okay, I'm going to show you a demonstration of a reaction of that kind, so you can see with your eyes like what they look like maybe to us. And then we're going to try to draw a picture at the molecular level of what's going on. Once again, so you can see the full picture of what makes something, once again, if we use the word synthesis, what makes something a synthesis reaction, okay? Okay, so first off, to start us off, don't say anything out loud. I want you to just think to yourself. There's a question box at the very top of this unit I want you to answer on your own, just to get our brains thinking. So the question says, why do atoms react? So from what you've learned in this class or other science classes, why do the atoms even link up? Why don't they just stay individual? What's causing atoms to come together? Write down any thoughts you have, whether right or wrong. As long as there's something in that box that connects to chemistry, you'll get a smiley face. Oh, don't let me forget, at the end of the day, to tell you about the November Smiley Face Challenge, where you can earn up to 20 if you complete the challenge. So, all right, so. Okay, fill in that box. Get your brain thinking. To the very top of topic 6. As long as you wrote something in the box that has something to do with chemistry, that's all I want to see. Just what thoughts do you have? Okay, raise a hand, anyone willing to share their thoughts on why do atoms form? Yeah, let's hear it. Good, there's definitely, like, if they're going to change, like, there obviously must be something that's, like, becoming better for them, right? Because otherwise, there'd be no draw at all. Now, obviously, atoms, as far as we know, don't have, like, feelings and things like that. But scientists have found that in certain situations, when things bond, they become a more stable state. Now, in other times, it's not more stable, which means those reactions don't happen on their own, right? They have to be, like, forced to happen, or they just never happen, right? But if a reaction will just naturally happen, like the ones I'm going to show you today, where literally I just pour them together or mix them together or something, if it just happens, well, then it's becoming more stable, right? I saw some of you others put things about their electrons, which, for whatever reason, we have found that a full outside electron shell is stable. Once again, this is kind of one of those questions of like, well, why is it? And I don't know if scientists really know. They've just found this pattern that, well, every time an outside ring gets full, the atom is less likely to react and it's more stable. Why? Once again, the noble gases, the farthest column 18, don't really react much at all because they're already full, right? And so they don't really have a need to bond with anything, okay? All right, so when we talk about a chemical reaction is a process that involves the rearrangement of atoms resulting in a new substance. Now, one question that some of you missed on the test was talking about this law of conservation of matter, right? When we balance a chemical reaction, we know things cannot be created and they can't get destroyed. The key word is they just rearrange. But what's so crazy with chemistry is how different something can be when it rearranges, right? Like, looking at this picture, it looks like, oh, it's not that different, right? Like, okay, these things are connected, and then now on this side, oh, look, now the black's connected with some red, so they're just rearranged. But what's crazy is these two things are completely different than these two things, right? Like, this is oxygen gas, we breathe it in. This is carbon dioxide, we breathe it out. But if you tried to breathe this in like oxygen, you would suffocate, because we don't breathe in CO2, right? Same thing, this is extremely flammable. This puts out things that are flammable, right? So like when they rearrange into H2O versus H with C, what they are and how they behave is completely different. And that hopefully you'll see a lot today when we look at the demonstrations with your eyes. I'll show you and kind of pay attention to like, this is what it looks like before, now look how it looks after, okay? All right, so first type of reaction that we are going to group is known as a synthesis reaction. If you think of the word just synthesize, it's used outside of chemistry. The synthesize is the creation of something. But by definition for a chemical reaction, it's two things becoming one. So in terms of like, if you don't want to think in chemicals, A plus B becoming AB is a synthesis reaction. Okay, so it's separate Legos becoming one big thing in the end. Okay? Now, here's an example, and this is the demonstration we're going to do. Okay, notice that it's Mg and O2, so they don't have to be like completely individual, but they're individual as like this side is now it's all connected. Okay? All right, questions on the pattern so far? All right, let's do the demo, and then we'll draw a picture too. Okay, so this right here, flies out. What's Mg? Magnesium. So this is magnesium. It's a metal. It's really, really malleable like most metals are, so I can bend it like a paper clip. It's pretty easy to bend. Okay? I'm going to make a little twisty cue here. Right? Looks like a metal, shiny, metallic. What am I reacting it with? Oxygen, right? So it's Mg, so it's this, plus O2. The oxygen is in the room, right? So this reaction actually is already happening because there's oxygen, there's magnesium. But some chemical reactions, and we'll have a whole unit about this, but some are very slow. And we don't have like 10 years, because that's how long this reaction will take for this to happen. So I'm going to do something to speed it up. But keep in mind, it's still the same reaction. We're just pushing it along because we don't have time, right? So one way to speed up a chemical reaction is with heat. So I'm going to light it on fire. And that will help. Okay? Now with this chemical reaction, I'm putting on goggles just because I'm close to it, right? So I'm close to chemicals. But for your safety, it is recommended that you don't stare directly at it. Okay? Now, what that means is I'll hold it. So I'll light it, and then I'll hold it right here. You can look like at the O, but just don't stare directly at the light. It's just not recommended for your retinas. So.
You're a baby.
looks like now. I made it too tall.
It's great.
Okay, so on your observations, which has that box that talks about observations from demonstration, I want you to make sure you talk about the before and the after, right? So what it looked like before, here's how it looks after. So this is what fell on the ground and why it fell versus what it was before. So this is our after. So this right here is now manganese oxide. It's what happens when they form together. It's not magnesium. It's not oxygen. It's magnesium oxide. Something completely different, and you can see by how it looks, it doesn't look anything like magnesium or like oxygen. Did I show the camera up close? No.
Whoa.
A lot of times if I don't make it too big, it won't like completely fall apart. And it kind of ends up looking like those twisty ties on bread. But it is like, it's a white powder is what it is, so. Okay, looking at your orange strips, I want you to see if you can pull out all the different synthesis reactions. Ready, set, go.
What?
So looking at the orange groupings, which ones, and if you get them right, you'll get a smiley face if you can find them. So look at the orange strips and sort out which ones are synthesis.
Air molecules. Outside makes it have lots of pressure.
All right, you got 10, 9, 8, 7, 6, 5. We have a whole top of
Yes.
good observation. 3, 2, 1. All right, which numbers are synthesis? So 4 is synthesis and 12 is synthesis, and I think that's it.
What? Yes. We're too good. But how are these?
Synthesis is 2 things. There you go. But you just found the next one. So you'll already be ready for that. Okay, questions on synthesis. Identifying if you see it. Okay, now in that second box, where we're drawing a picture at the molecular level, this is somewhat up to you. And I'll give you an example for this first one, but like it's really up to you. Once again, our big theme for this whole term is all about developing and using models. So you're creating a model that represents a synthesis reaction more in a picture form than a symbolic form. Once again, it's showing the same thing, but sometimes that picture form connects better to people than a symbolic form does. So for this one, what I would maybe draw for my synthesis at the molecular level is I always like to visualize atoms as just little bouncing balls. So in that box, I would draw maybe by different colors, or if not, you could do like different shapes. So it'd be like this is the before, and then the after is them now connected. So that would be kind of like what's happening at the molecular level. Once again, chemistry is so weird because like literally like this doesn't seem that different from this. But it's so crazy when the Legos stack, how different things become. opposite of a synthesis. So synthesis is 2 becoming 1. Decomposition is 1 breaking up into 2 or more. Technically it doesn't have to be 2, but it's just starting with 1, becoming multiple. Once again, this one by name should help make sense, because for something to decompose, it means it's breaking apart. And so the same thing happens in a chemical reaction, is it's one thing becoming multiple things. Okay? Alright, so our demonstration here. So this right here in this brown bottle, this is H2O2. Hydrogen peroxide is its name. You might have this at your house. Also typically comes in a brown bottle. Normally they're rectangular. Right? And you pour this like on your cuts. And it stings and it bubbles, but it's really good at like cleaning it out, right? The difference though is this one is a 30% solution. The ones you buy from the store are a 3% solution.
Oh my God.
So yeah, this one you don't pour on cuts because it would definitely hurt a lot. Because this will hurt on your skin if it's not cut. Now, do I need anything else for decomposition?
Yes. No, you don't.
I don't, right? It's just one thing. That's why this is stored in a brown bottle. Is what causes this to decompose is light. Is when it's exposed to light, it naturally becomes water and oxygen. So that's why it's stored in a brown bottle, is to try to slow that process down. But actually, if you look even at the ones at your house, they have an expiration date on them. Because over time, it is slowly happening. And so after so many years, you don't have hydrogen peroxide in a bottle anymore, you just have water. Yeah.
Oh, you can drink it?
Well, theoretically, yes. I don't know if I would. But the other interesting thing is, when I buy, the ones at the store don't do this because it's only 3%. But because this one's 30%, when I buy these, they're only filled about this much with liquid. Because what else gets created when it decomposes? Oxygen. And if it didn't have space for the oxygen, the bottle could explode. Yeah. I'll have to show you, they used to send them in these actually really cool, I'll go grab one, I have them, these really cool like accordion bottles that can like stretch. So like as the oxygen, so what happened is sometimes over the summer, I'd come back and one of the bottles would be like super big in my closet because I'd like spread it over time. Now, once again, this reaction isn't fast, even when I bring it out of the bottle. So I'm gonna add something to it so we can see it happen faster. This time I'm not gonna use heat to speed it up. I'm gonna use something known as a catalyst. Once again, in our unit where we talk about rates of reactions, we'll learn about catalyst. But for now, catalyst is just something you can add that pushes the reaction along, but it's still there in the end. That's why it's not in the reaction, because it's you start with it and you end with it. So catalysts are great, like you can recycle them and reuse them over and over and over again. But it just pushes it along. Otherwise, like it's happening, and you can see like tiny little bubbles going on, but you know that's not very exciting. So, okay, so this is my catalyst. So notice your before observations of what hydrogen peroxide looks like. Okay. And then here we go. Ready? 3, 2, 1.
Whoa. Whoa. That's crazy. Well, that's sick.
I know that looks cool with the projector. So what were the two things we were making? Water and oxygen, aka a cloud. Where's the smoke detector? It's not actually smoke, it's just vapor. But it's been a very long time. It doesn't last that long. But that's why like it's not harmful to breathe in because it's literally just water and oxygen gas, right? Now, what's left in there you'll see is like dark. It didn't turn it dark. The powder I added was dark, and as a catalyst, I could filter it back out so I could like pour it into like a filter paper. The liquid would go through, I could catch the powder, and then I could literally do the same thing with the powder next, period. Because catalysts aren't part of the reaction, they just make it go faster. So it is also, we'll learn next time about how some reactions create heat, and and this one creates a lot. So the bottle's actually quite word now, so I'm gonna give it a second before I touch it. So, okay, looking at your orange strips, find me the decomposition reactions. Ready, go. So pull out the decomposition reactions. Do you feel like you can breathe better now, Cam? Get all that extra oxygen.
Yeah.
Okay, everyone have their decomposition ones decided? I think there's 3, if I remember right. Oh, there are 4? So you should have 7, 14, 9, and 2.
Yes.
Do you have all of those? You can have another smiley face. Good job. Okay, ready for the next pattern? Alright, so our next classification is known as a single replacement reaction. Okay? Now I want you to label something extra on this just to emphasize it, okay? In a single replacement, you have an element by itself. Meaning just one capital letter. It's just one thing over there. You then have it reacting with a compound or a molecule is what you call them. Compound is when you have multiple elements linked together. In a single replacement, the single one switches out the place of one of the ones in the grouping. So notice it was A was by itself, B was with X. Now, A is with X, and B got picked out. Right? Okay? Questions on that pattern? Okay, so what I have up here, so we have Zn, which is zinc. So here's zinc metal. We've worked with it a few times in the lab you guys have yourselves. Okay, so that's zinc metal. Okay. I'm going to react it with hydrochloric acid, which is HCl. And who's getting replaced? Yes. Yeah, I mean, depending on how strong it is, but yes. Most acids are. It's actually, hydrochloric acid is the acid in your stomach. So like that feeling of your esophagus burning.
Oh, I hate
That's because of hydrochloric acid. Okay, hydrochloric acid before looks like water. Okay? Now, we're making is zinc chloride and hydrogen gas. Now, last time I didn't cover it because it released oxygen gas, which is fine for us to breathe. We don't really want to breathe in hydrogen gas. It's kind of irritating. So I am going to put a balloon over the top of this reaction just to catch the gas it's creating so we don't breathe it in. Okay?
Oh.
Make sure.
Here's the balloon put on. This guy.
You wouldn't die instantly. You wouldn't really die from it. It just would make you cough a lot. So you can kind of see as it's reacting. Once again, notice how they look before. Things that are changing that tell you a new substance is being created. Right, the atoms are definitely rearranging. They're not just like mixing with each other. Another common theme to chemical reaction is change. That's kind of another good indicator that like new things are being made. Okay, so write out your observations, come up with a model for yourself. Let's go. Set that right there. Yeah, Lincoln.
So could it go from AX plus B to A plus BX?
Yes, that would still be classified as a single replacement. Yeah, good observation. We won't do it a ton, like, 'cause in this class you just need to look at the whole picture, but it's all about really, if this is a metal, it's gonna switch out the metal. If it were a non-metal, then it would switch out the non-metal, so yeah. Okay. 4, everyone got those filled in? Alright, go to your orange strips and find all the single replacements.
This one's long. Right? Right. Do we know how many of these there are?
Nope. Not off the top of my head. Oh, that one's getting really big. I don't want to
Oh, this is.
Okay, wave your arm if you need more time to sort your orange strips. I'll give you like 10 more seconds. Okay, so for single replacement, you should have found number 3 is definitely a single replacement. Number 5 is a single replacement, and that's all I see. Anyone have another they think is?
Is 13 one?
Oh yes, 13 as well. Yep. So 3, 5, and 13 are your single replacements.
Why is it 11?
Number 11. Ooh, good. 11's tricky. So the difference is, so it is like compound element, but then notice on that side are either those a single thing.
No.
So it has to have like, it kicks out something single. But it is close because like the left side of it kind of matches, but the right side doesn't. So. Okay, any other questions about single replacement? Identifying those ones? Okay, similar. Now, double replacement. So double replacement is, once again, same concept, but now it's like 2 dancing, and then they switch partners. Right, so A is with X, B is with Y, and then notice A pairs up with Y, and B pairs up with X. So double replacement, 2 compounds switching their partners. And it does in this case kind of go with what Lincoln asked before. In a double replacement, it is always the same, where the outsides pair up and the insides pair up. That pattern never changes. Okay, ready for our demo? Okay, so few things, and some of you noticed this before. When we look at a full chemical reaction, we can label the states of the matter, which can sometimes just give you more information. AQ is the symbol for aqueous. So this means this has been dissolved in water. So this is normally salt, but with an AQ next to to it, that's why it looks like this, is because it's salt water, right? So notice it's aqueous, 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 solid. So little s is for a solid, okay? All right, so the befores, they pretty much look like water because they're both dissolved in water. But, okay, are you guys ready? This one goes quick.
Uh-oh.
All right, ready? So as soon as I pour it in, it will do its thing.
Whoa.
So definitely not the same thing we had before, right? Now, so I'll bring it around so you can get a closer look. So this is how you make orange juice on your own.
Don't.
No.
Wait, no, he said it's green.
So what will happen, I'll let this sit. So what we've created is actually a yellow powder. That's why the whole thing looks yellow. It's similar to like if there's mud and you step in the mud and then it turns it all brown. So it looks all yellow, but it's just there's a yellow powder in the water. So I'll let it sit, and if you don't touch it, what will happen is the powder will all settle to the bottom, and you'll actually be able to see it separate from the aqueous solution that it's in, right? So what we've created is this solid substance, but it's floating around in this aqueous substance, so it looks like that. So, questions on double replacement? Okay, find them with your orange strips for a smiley face. And hopefully we find these correctly. By default, it's going to find the last one, right?
We got one.
All right, did we decide on our double replacements?
Yes.
Think so? Okay, double replacements, you should have found number 1 and number 6. And number 8.
Yes.
Number 1, number 6, and number 8.
Oh, bro, one's floating. Oh, what the?
Questions on any of those, of like you identified one that's not, or why one is?
Wait.
Close. What did we make? It's close to helium. Hydrogen.
Hydrogen floats.
Because it's also really light, right? Just has to be lighter than O. So anything lighter than oxygen will float.
Carbon? Carbon floats?
Well, it's not a gas though.
Oh, yeah. Hydrogen floats.
Yeah. Okay. Good. Okay. Looking at your last grouping. So the ones that pretty much have sorted themselves out, what ones have we not grouped? Number 10 and 11. What pattern do you notice about 10 and 11? Good. So on the left side of the equation, they both have oxygen. What else do you notice? What's on the right side? Yeah, so this one is, it's almost the most specific of a reaction because it's not so much about a generic like A-B pattern, but there's very specific things that are always used and always created. So the last type of reaction we have are known as combustion reactions. Combustion reactions always have oxygen as a reactant. You have to have oxygen. C, H, and O, right? But it has to have C and H. We call them a hydrocarbon. Now the amount of C and H's don't matter. It just has to have some C, some H, and it has to react with oxygen. Then it always creates carbon dioxide and water every single time. Now it could create other things too. In some like more complicated combustions, you can have other products, but you're always going to have this, this, and this every single time in a combustion. Okay? Questions on identifying combustions? Well, do you know what little G would mean? It's a gas. So, but I guess if we track the gas, oh, actually, have you seen The Martian?
Yes.
So you know, like in The Martian when he creates rain,
Yeah.
he does it through a combustion reaction. So he does a combustion, and then he catches it, and then it rains back down. So, sure, you could drink it, I guess. Ours is gonna go away, but otherwise you can.
That is so cool.
Okay, so this right here is the gas we're gonna use. Okay, the oxygen's in the air. Now,
That is so cool.
okay, now for this reaction is another one that needs a Kickstarter to get going. So we're also going to use heat to help this out, so we're going to use some flame. But what I want you to notice is we only have to put a tiny bit in, a little bit of heat, but then everything else it just does on its own. Right? Like I don't have to keep putting more heat in, I just give it a little spark, and it will go. Now to help in this demonstration, because this is a gas, I'm going to trap my gas in bubbles, because otherwise a gas would just float away, right? So this right here is just soapy water in my funny little contraption I made. Okay? So I'm going to fill the soapy water up with the gas. The oxygen is in the air. We're just going to use a little bit of heat to help it get going. Okay? All right. Cam, are you comfortable lighting a match?
I am.
Mason, can I trust you?
Yeah,
Okay,
sure.
come on up here, Mason.
Yes! Yes!
Oh, yeah. Let me grab, I thought I had a match over there. Let me grab a match.
Yeah.
I don't think you're trustworthy last night.
Glad to match.
Yeah, really.
Stand-up comedy.
Check what's in the sink. There's something smoking.
Oh, it's the. Pretty sure it's the. I shouldn't read that. Oh well.
Take those. Oh, I should probably get you guys.
Light one for fun.
Oh, no.
Practice.
I was practicing. That was the wrong joke. It is.
Try the other
I
side,
can
yeah.
smell it.
Don't worry, it's pretty safe.
Try the other
It's
side.
no, I can smell it. Smoke.
Dude, it's gonna light a fire. Rub it the other way.
Dude, the trash can's going to light on fire now.
Those are flammable.
Okay, so what's going to happen is I'm going to push up the bubbles. I'll be holding my hand like this, and you're just going to light a match and touch the bubbles.
Hey, I was trying to light a match earlier and I couldn't do it.
Oh dear. Sorry, I believe
my
it.
best.
Try a different
And
spot
just
of
do it from
why don't you
like
sit that lighter
arm's
that's right
length,
there?
because it's going to be warm. Okay, so let's get some bubbles made.
Go on the roughest spot.
Yeah, it shouldn't matter.
Whoa.
Okay. That looks like good.
Better not mess this up, Mason.
All the pressure. Okay, ready?
Come on. Dude,
You can do it.
come on now.
Hurry, dude.
So, once again, the bubbles were just to hold the gas, right? And then, once again, we only had to use a tiny flame, and then all that extra heat was the process of this chemical reaction happening, right? Now, in case you're wondering, I'm not a firebender, but, no, not at all. So, first off, the reason why it doesn't hurt are two reasons. One, what did I do? Did I do with my arms before? So I put soap and water. Water does a really good, is very slow at absorbing heat, so it's a really good protector. The problem is eventually it will evaporate, right, so it can like be protected forever. But as long as my arms are wet and soapy, it protects me from the heat. So it's warm, like Mason, you even can, you guys can probably feel it. Like, it's warm, but like, it's even less like, the pumpkin I lost some arm hairs with, but like this one, like, nothing at all. And then the other reason why is because it burns so quickly. So otherwise, if it was slowly burning, then sometimes it can get quite warm and I have to shake it off. But that is combustion reactions, and all combustion reactions have flame.
Is it just me or does it smell like after that you like you bought your candles for your birthday or something like that?
Probably, yeah. Okay, any questions on our 5 different classifications?
I want to do that now.
How can you
Okay, last, we got a bonus combustion we can do here. I need a stick. So our balloon is filled with what? Hydrogen. There's oxygen in the air. So if we add a little bit of heat to our hydrogen, we can also get it to combust.
Guys, it's harder than it was, alright?
It's a pretty worn out box, I'll give you that. It's been well used.
Oh, we already did this. We did this at the beginning of the year.
Yes, very glad you remember.
Oh, that means we don't have to do it.
Should I just leave the balloon there? You already know what's going to happen. Okay, ready?
No.
Are we going to wake Josie up?
You got deep sleep. Oh, there's a smoke ring. Oh, it was.
Oh, wow. Look at it in the, you can see it in the protector. So. All right, so your... All right, so you don't need to, I'll come around and check, I already kind of checked these. This isn't something you need to submit online because there's just our warm tape, so I just kind of checked it as you were doing and I'll put it in Canvas. Your homework assignment is right after it, classifying reactions. So I give you a reaction, you gotta tell me what kind it is. Now, these are also balancing practice problems, okay? Now, there are a lot of them. You are only required to balance half for like full points. Anything more than that, you can get extra credit for if you want to do more balance.
7 or 8?
Oh, we'll go 7. So balance at least 7 of your choice, and then if you want to balance more for extra credit, you can. Okay? All right, go ahead and get started. Let me know if you have any questions.
I'll take it.
I don't know.
Is it already done? Oh, that makes you think you found out. We had it right now.
Oh, I guess I can stop this.